Hello students, welcome to BTech first year physics course. In the last lecture, I have discussed about physical interpretation of divergence of any vector field, right? Now today, I am going to discuss Stokes theorem and concept of curl. Okay, so let's start. The theorem is named after Irish mathematician and physicist Sir George Stokes. And what we call Stokes theorem was actually discovered by Scottish physicist Sir William Thomson. Stokes learned of it in a letter from Thomson in 1850. Okay, so this was the history of Stokes theorem. Now, if we talk about its application, then we must say Stokes theorem plays an important role in fluid mechanics, electrostatics, magnetostatics, especially in Ampere's law, then electromagnetic induction. Okay, so let's understand the theorem. It tells that the line integral of the tangential component of continuous vector field A taken over a simple closed curve C is equal to the surface integral of the normal component of the curl of the vector field taken over any surface having C as its boundary. Okay, and in mathematical form we can write like this. Now here the direction of the line integral along the curve is considered as positive direction. So what it means? It means if an observer walks on the boundary of the surface in such a way that the surface on his left side and his head pointing in the direction of positive normal to the surface. Okay. Next, we have to understand what is curl of a vector field and how we can express it in mathematical form. Then we will prove Stokes theorem. Okay, so let's proceed. So first, consider an infinitesimal rectangle of sides del y and del z in yz plane. And P is the middle point of this rectangle. And its position is x, y, z. Now suppose a vector field A is passing through this rectangle and the form at P is like this. Then the line integral of the vector field along the path A, B, C, D, A is given by like this. As the starting point and end point are same, this is also called closed line integral of the vector field. Right? Here dl vector is j dy plus k dz as the rectangle is in yz plane. Now we can decompose the closed line integral into these four line integrals along different paths. Now you see along AB dl vector is j dy along positive y axis, along BC k dz along positive z axis, along CD minus j dy opposite to positive y axis, and along DA minus k dz along negative z axis. Right? Now we have to solve these integrals. So let's solve the first integral. Here a2 function of x, y, z minus del z by 2 denotes the component of a vector at the midpoint of AB path in the direction of positive y-axis. Because just below P point, here the coordinate is x, y, z minus del z by 2. And the length of AB varies from minus del y by 2 to plus del y by 2. Now this A2 function of x, y and z minus del z by 2 can be written like this. A2 minus del A2 by del z then multiplied by del z by 2, which is the length from P to the middle of AB, right? And why is this minus sign coming? Because the midpoint of AB is del z by 2 distance below of P point, and after integration we get this. Okay. Similarly, along CD, BC and DA, the value of integrations are like this. So total closed line integration along AB, CD, A path will be addition of all the 4 terms, and we get this. Del A3 del Y minus del A2 del Z multiplied by del Y del Z. And this term is actually the x component of curl of A. Then this x component of curl of A can be written like this. And condition is the limit s tends to 0. It means this expression is valid only in the limit as the rectangle shrinks to P point. Right? Then similarly, y component of curl A will be del A1 del Z minus del A3 del X, and z component of curl A will be del A2 del X minus del A1 del Y. Now if we add these terms in component wise, we get this form of curl of A, and this can be written like this form also. Okay, so this is similar to A cross B, cross products of two arbitrary vectors. Only difference is instead of the first vector we have del operator, and you know del operator is I del del x plus j del del y plus k del del z. Then we get del cross A. Now let's understand the physical interpretation of curl of a vector field. In vector calculus, the curl is a vector operator that describes the infinitesimal rotation of a vector field in three-dimensional space. Now at every point in this field, the curl of that vector field is represented by another vector, and that is perpendicular to the plane of rotation of the vector field. Okay. So the direction of the curl is actually the axis of rotation of the vector field, and this can be determined by right hand rule. Now here the direction of the thumb is indicating the direction of the curl, and direction of tip of other fingers is showing the direction of rotation. Now the magnitude of the curl is the magnitude of rotation of the vector field, and that is measured by the length of the new vector along the axis of the rotation, which is the thumb direction. Okay. Now if a vector field represents the flow velocity of a moving fluid, then curl is the circulation density of the fluid, and we can quantify the curl of a vector field by this equation for this small loop. Next, we have to prove the Stokes theorem. So to do that, let's consider a surface S like this, and it is bounded by the curve C. Then let's divide the surface S into n numbers of elementary rectangle or square. And let's say area of such an element is del Si. Here I represents the ith element. Okay, and the boundary curve is Ci. Then the line integral of the vector A around each of the paths in anticlockwise direction can be written as closed line integral A around Ci curve is equal to curl of A dot Ni del Si. Here Ni is the unit normal on del Si surface. Okay, and I varies from 1 to n. Then if del Si becomes infinitely small and n becomes infinitely large in number, then summing over all such possible line integrals on the surface S in the same direction, same anticlockwise or positive direction, we get the line integral around perimeter C, which encloses the total surface S. Because all parts of line integral around the surface elements cancel out except the parts which are along the perimeter C, that doesn't cancel out. Okay, and we get this complete form of Stokes theorem. Okay, so that's all for today's class. In the next class, I shall discuss few problems and solutions related to Stokes theorem to show you how you can apply Stokes theorem. Okay, so thank you for attending today's lecture. See you in the next class.